Hi students, welcome back to our physics classes. So during the last class we have seen how you can bias a PN junction and what is the need of biasing in PN junction. And we have seen whenever a PN junction is formed, there is no current flow across the junction. If you want to make current across the junction, you have to bias it. You can bias a PN junction in two different ways. One is forward biasing and the other is reverse biasing. In forward biasing, you are accelerating or you are supporting the majority charge carriers to cross the junction, and in reverse biasing, you are supporting the minority charge carriers to cross the junction. In majority supporting, that means in forward biasing, we will get a measurable amount of current, and in reverse biasing, we will get a negligible amount of current. Anyhow, we can say that whenever a PN junction is forward biased, it is offering a low resistance to the current flow across the junction, and when a junction is reverse biased, it offers a high resistance to the current flow. So that is the biasing of a conductor, that is forward biasing as well as reverse biasing. So we have to see when you are having a diode and the diode is forward biased or reverse biased, what will be the nature of VI characteristics of a diode. We have to see VI characteristics of a diode in forward bias as well as reverse bias. So we can go for that. So we can plot a graph between voltage and current across a PN junction under forward bias. You know how we can forward bias a PN junction. This diagram shows how you can make a PN junction in forward bias. So this PN junction is forward bias and the biasing potential can be adjusted by this rheostat. So initially when the potential biasing potential is, we have already seen that why biasing is required to overcome the barrier potential. So when you are considering a germanium crystal, in germanium crystal the barrier potential is 0.3 electron volt, 0.3 volt means not electron volt, it is not potential, it is only a barrier potential. So 0.3 volt is the barrier potential. So if you are, suppose you are taken a silicon crystal, silicon diode, then it is 0.7 volt is the barrier potential. So when you are slowly increasing the biasing potential, you can find initially there is no current. So when the barrier supply potential is equal to the barrier potential, that is 0.3 in case of a germanium, then after that if you are supplying the barrier biasing potential, you can find current is abruptly increasing, which means up to the barrier potential we are not having any current because the charge carriers are not enough energy to overcome the barrier potential. So they can't make any current through the junction. So when the supplying biasing potential is equal to or greater than the barrier potential, then only it provides you a current across the junction. So this value for the biasing potential, is known as knee voltage. So what is knee voltage? Knee voltage is the value of biasing potential which is numerically equal to the barrier potential. So this is the case when a junction is forward biased. So when a junction is forward biased, the VI characteristic is like this only. That means whenever you are slowly increasing the biasing potential, initial stages there is no current. When the biasing potential equals the barrier potential, then current starts. When we are increasing the biasing potential above the barrier potential, then you will get enough current in the forward biasing, because at that time the barrier potential, that means the depletion region width decreases, barrier potential decreases, net potential will be VB minus VA. VB is the barrier potential and VA is the applied potential. Okay, so current is flowing through, and the same circuit you can go make use for reverse biasing. How you can make reverse biasing? You can make it in the opposite sense. That means if you are connecting N region to positive and the N region to negative, P region to negative, then you are getting a reverse biased junction. So when you are having a reverse biased junction, now it is in the reverse bias. So what will be the reverse bias? Means the potential is applied in the negative sense, and current formed is in the reverse direction. So you can take it as reverse current in the opposite direction. See again, when you are applying the applied potential, you will get a VA character like this. Why like this? Because when you are increasing the biasing potential in the reverse bias, depletion width region increases. Only minority charge areas are providing the current there. So slowly, whenever the depletion region width is sufficiently enough to accelerate the more and more minority charge areas, then only you will get a current across. So after this, the current increases. After a particular value for the biasing potential, the current increases. Okay, so that voltage is known as the breakdown voltage. That voltage is known as the breakdown voltage. So at breakdown voltage, what will happen? The width of depletion region increases and the depletion region breaks. Depletion region breaks means we know at the depletion region minority charging areas are in the bound state. At the depletion region, minority charging areas are in the bound state. When you are supplying a reverse biasing, the width of depletion region increases. It reaches a condition at which the voltage developed across the depletion region is sufficiently enough to break the covalent bond present between the minority charging areas with the opposite charges. So what will happen? The covalent bond between the minority charging areas and the opposite charges is breaking up. Minority charging areas are free across the junction, so they will cross the junction with the help of reverse biasing. Then current abruptly increases, and that particular voltage of the biasing potential in which the breakdown of the depletion region happens, and that voltage is known as the breakdown voltage. So two voltages you have to remember here: knee voltage in forward bias, breakdown voltage in the reverse bias. Knee voltage in the forward biasing is the value of biasing potential which is equal to our barrier potential. Here breakdown voltage is the biasing potential at which the depletion region breaks and the minority charging areas which are already in the bound state become free and they will cross the junction to maintain a current. Anyhow, it is due to the minority charge, so in the reverse biasing current is obtained in the microampere region. It will be obtaining in the microampere region. So again, from this description it is clear that whenever a PN junction is forward biased, it will be offering low resistance to the current flow and it will be in the conducting state. When you are having a reverse biased PN junction, it offers high resistance to the current flow across the junction, and in that sense it is a non-conducting state. So that is forward biasing and reverse biasing. Since we have seen whenever a PN junction is in forward bias, it is in a conducting state. When it is in the reverse bias, it is in non-conducting state. And this property helps us to use diode in some particular practical circuits. And one of it is a rectifier. Circuit. What is a rectifier? We have seen two types of voltage and two types of currents are available, which are the AC voltage and AC current and DC voltage and DC current. What is the difference between AC and DC? AC flows in alternate directions, that means opposite direction alternatively, and DC flows in the same direction. Many of the situations we need DC current. But in our households we are getting AC voltage, or from that AC voltage we have to convert into DC. How you can convert AC into DC? Its answer is this rectifier. So this rectifier circuit changes AC voltage or AC current into DC voltage or DC current. And the main ingredient, that means the main circuit element of this rectifying circuit is diode. And why we are using diode? We know when the diode is in the forward bias, then only it is conducting. When it is in reverse bias, it will not conduct. So using this property, we can design a rectifying circuit which can convert AC voltage or AC current into DC voltage or DC current. There are two types of rectifiers. One is half wave rectifier and the other is full wave rectifier. Half wave rectifier and full wave rectifier. Half wave rectifier gives you DC output only for 1/2 cycle of AC input. Rectifier, its input is AC voltage and its output we are getting as a DC. And if you are applying a full AC cycle, that means a positive half cycle and negative half cycle to a rectifying circuit, if you are getting only output only for a half cycle, then you can say that it is a half wave rectifier. That means half of AC wave is rectifying. Rectifying means it will provide you only voltage or current only in one direction. That means if it is positive half cycle only passing out, you will get only positive half cycle. Negative half cycle is not available in the output. And in full wave rectifier, what happens is you are getting output for full AC cycle, which means both positive half cycle and negative half cycle, which is turned into positive half cycle, will be available in output. So there are two types of rectifiers, half wave rectifier and full wave rectifier. We will see both separately. What is the working of half wave rectifier and full wave rectifier? This diagram shows a half wave rectifier practical circuit. See, here you have a transformer. What kind of transformer? It is step down transformer. Since the number of turns in the secondary is less than the number of turns in primary. So here input of an AC source is given to the primary of this transformer. It is in the step down form available in the secondary of this transformer. Suppose positive half cycle is coming first. Positive half cycle of AC is coming first. At that moment, see, these are the 2 points in the secondary of the transformer. B is already grounded. Grounded means it is at zero potential. So, during the positive half cycle, the point A will become positive with respect to B. A will become positive with respect to B during the positive half cycle. So, A is positive and it is connected to the P region of the diode. So, what will happen? It is in the on state, that is on state means it is in the conducting mode, it is in the forward bias. It is in the conducting mode, current will flow through the load resistance RL where you are getting an output. So, this is your input and during positive half cycle you are getting output. So this is output and this is input. Okay, so for positive half cycle of AC input you are getting an output across the load resistance RL. Now after this positive half cycle, what is coming next? The negative half cycle is coming. So when negative half cycle is coming, already B is at a zero potential, A will become negative with respect to B. Now, negative potential is given to P region. What will happen? It will be in the reverse state, reverse bias state. Diode is in the off state, which means it will not conduct. If it is not conducting, no current is flowing through the diode, no current is flowing through RL, and no voltage is developed across RL as VO. So during negative half cycle you are not getting any output. After the negative half cycle, what is coming? Positive half cycle. At that moment A will become positive, then it will become on state, then it is conducting and you are getting output, which means during positive half cycles of AC input only you are getting output. Negative half cycles are not there, the negatives are rectified there, but you are not getting output during the negative half cycle. So we can say that it is a half wave rectifier. It is a half wave rectifier. Okay. See, now I have made some changes in the diagram. What are the changes you can find out? Earlier, there was only 2 points in the output in the secondary of the transformer, that is A and B. Now, one more point I have taken, that is C. So, this is a special kind of transformer with 3 leads in the output, which is known as the center tapped transformer. Center tapped transformer. Center tapped transformer means in the secondary you will get 3 points. Middle point is grounded. Middle point is grounded means middle point is always kept at the 0 potential. So with respect to C, simultaneously A can be positive and B can be negative. Okay, that is a property of 3-leaded secondary transformer. That means with respect to C, A is positive and B can be negative, and A can be negative and B is positive with respect to C. Instead of one diode, we are having 2 diodes now, and these two output of these 2 diodes are connected together, and across that we are connected RL between ground and the end of these 2 diodes, and across which we are getting the output VO. Okay, now we can see the working. Again, the same AC potential is given. During positive half cycle, point A will become positive with respect to C. At the same time, B will become negative. That is a property of a center tapped transformer. If one lead is positive with respect to C, automatically the other will become negative. So this is D1 and this is D2. So D1 is connected to the positive potential and D2 is connected with the negative potential. So D1 is forward bias and D2 is reverse bias. D1 will conduct and current is flowing through RL, and you are getting a output in the across the load resistance RL due to the conduction of D1. Are you getting me? See, next negative half cycle is coming. During the negative half cycle, A will become negative and B will become positive with respect to C. If A is negative, then D1 is in the reverse bias and D2 is in the forward bias. So what will happen? D1 will not conduct and D2 will conduct. So see the direction of current flow from D2. It is coming through the same direction across RL, and it can provide a potential VO. So during the negative half cycle also you are getting output across RL, which is due to conduction by D2. Okay. Now after that positive half cycle comes, A will become positive, B will be negative with respect to C, D1 conduct. Next negative half cycle, what will happen? D2 conduct, which means during the whole cycle of AC, that means during both positive half cycle as well as the negative half cycle, you are getting output across RL. Now you can say that it is a full wave rectifier. It is a full wave rectifier. So that is the difference between a half wave rectifier and a full wave rectifier. In half wave rectifier, we are getting only output only for positive half cycles, only one half cycle of AC input, but here you are getting output for both the half cycles of AC input. And remember, both will appear as positive half cycles in the or positive, or the current is flowing in the same direction only in the across the output. So that is, you are converting AC into DC. That means negative half cycles are cutting in half wave rectifier. In full wave rectifier, that negative half cycles are also converting into positive half cycles. So you are getting output for full AC in full wave rectifier. In half wave rectifier we are getting only one half cycle in the output. So that is one of the application of half wave diode in the case of a rectifying circuit. In the case of the half wave rectifier, in the form of half wave rectifier and full wave rectifier. Okay, now we have seen what is a diode and one of the application of diode, and a small topic is left, that is different types of diodes. Different types of diodes means only 3 types of diodes you have to discuss. We have discussed, that is light emitting diode LED, then photodiode and solar cell. So that is our last topic, and that I am leaving for the next day. So we are winding up today, and we will meet in the next class.